For decades, we've treated the cosmos as though it were largely finished, a vast museum where stars burn predictably, galaxies rotate according to established rhythms, and the fundamental forces shaping existence remain essentially constant across the eons. But between 2024 and 2025, a series of observations began quietly dismantling that comfortable certainty. Instruments peering into the farthest reaches of space and time started revealing something unexpected. The universe appears less stable, less predictable, and far stranger than our most sophisticated models had suggested. Beneath the familiar constellations and within the light from impossibly distant galaxies, evidence emerged that challenges our understanding of how energy itself behaves across cosmic time, how black holes form in the universe's infancy, and whether the signatures we associate with life might exist in places we never thought to look. This is the story of how, in the span of just 2 years, astronomy experienced not a single revelation, but a cascade of them, each discovery opening new questions about the nature of reality itself. The distance. We cannot quite imagine, when astronomers speak of looking back in time, they're being literal in a way that never quite loses its philosophical weight. Light travels at approximately 299,792 kilometers per second, roughly 186,282 miles per second, which means that observing distant objects is fundamentally an act of archaeology. The photons arriving at our telescopes tonight left their sources years, centuries, or millennia ago, carrying information about conditions that no longer exist. In December 2025, this principle reached its most extreme application, yet when scientists announced the detection of a supernova explosion that occurred when the universe was less than 1 billion years old. To put that in perspective, the universe is currently estimated to be 13.8 billion years old, meaning this stellar death happened when cosmic time had advanced only about 7% toward the present moment. The event was first detected on March 14, 2025, not as visible light but as a gamma-ray burst, an intense flash of high-energy radiation that lasted several seconds. The Space-Based Multiband Astronomical Variable Objects Monitor, or SVOM, recorded the burst from its orbital vantage point, triggering an immediate cascade of follow-up observations. Within hours, the European Southern Observatory's Very Large Telescope in Chile was studying the burst's afterglow, using spectroscopy to measure how much the light had been stretched by the expansion of space during its journey to Earth. That measurement, called redshift, indicated the source lay at a distance so profound that the light had been travelling for more than 12.8 billion years. What makes this discovery particularly significant isn't merely the distance involved, though that alone represents a new record. Rather, it's what the observation reveals about stellar evolution in the early universe. For a star to explode as a supernova, it must first form from clouds of gas and dust, accumulate sufficient mass, burn through its nuclear fuel, and reach the catastrophic endpoint of its life cycle. All of this must happen within less than 1 billion years of the Big Bang, a time frame we once considered too brief for such massive stars to complete their evolution. The existence of this supernova tells us that star formation in the young universe proceeded more rapidly and perhaps more efficiently than our models had predicted. The decisive confirmation came approximately 110 days after the initial gamma-ray burst, when the James Webb Space Telescope turned its near-infrared camera toward the region. JWST's instruments are specifically designed to detect infrared light, which is crucial for studying the most distant objects, because the expansion of the universe stretches visible light into longer infrared wavelengths. The telescope's observations allowed researchers to separate the fading light of the supernova from the much dimmer glow of its host galaxy, a technical achievement that represents years of engineering refinement and calibration. Without this capability, the supernova would remain entangled with the background light, impossible to study in detail. The technology behind the vision, Understanding how we observe objects at such extreme distances requires appreciating the extraordinary instruments that make these discoveries possible. The James Webb Space Telescope, which launched in December 2021 and reached its operational position about 1.5 million kilometers from Earth, represents perhaps the most sophisticated astronomical instrument ever constructed. Its primary mirror spans 6.5 meters in diameter and consists of 18 separate hexagonal segments made of gold-plated beryllium. Gold was chosen not for its aesthetic qualities, but for its exceptional reflectivity in infrared wavelengths, while beryllium provides the necessary strength and stability at the extremely cold temperatures where the telescope operates. JWST orbits at what's called the second Lagrange point, or L2, a location where the gravitational influences of Earth and Sun balance in such a way that the telescope can maintain a stable position relative to both while remaining in perpetual shadow. This configuration is crucial because infrared astronomy requires extreme cooling. The telescope's instruments operate at temperatures around -233 degrees Celsius, or -387 degrees Fahrenheit. At these temperatures, the telescope's own heat signature becomes negligible, preventing it from overwhelming the faint infrared signals from distant cosmic sources. The detection of the record-breaking supernova involved a careful coordination between space-based and ground-based observatories, each contributing unique capabilities. SAVOM detected the initial gamma-ray burst, an event lasting only seconds but releasing more energy than the Sun will emit in its entire 10 billion-year lifetime. Ground-based telescopes then measured the redshift, determining the distance. Finally, JWST provided the detailed infrared observations necessary to confirm the supernova's nature and study its properties. This collaborative approach reflects modern astronomy's increasing reliance on multi-instrument, multi-wavelength observations that build comprehensive pictures of cosmic phenomena. The engineering behind JWST's sunshield alone represents a remarkable achievement. This 5-layer structure, each layer thinner than a human hair, creates a temperature differential of more than 300 degrees Celsius between the hot side facing the Sun and the cold side where the instruments operate. The sunshield spans roughly the size of a tennis court when fully deployed, yet had to be folded origami style to fit inside the rocket during launch. The precision required for its deployment, which occurred over several weeks following launch, demanded that hundreds of individual mechanisms function flawlessly in the harsh environment of space, with no possibility of hands-on repair. The physics of stellar death in deep time. Supernovae are not all identical events. Astronomers classify them into several types based on their physical mechanisms and the elements visible in their spectra. The supernova detected at such extreme distance appears to be what's called a core collapse supernova, the death of a massive star that has exhausted its nuclear fuel. To understand why such an event matters for our understanding of the early universe, we need to trace the life cycle that leads to this catastrophic endpoint. Stars form when vast clouds of hydrogen and helium, the primordial elements created in the Big Bang, begin to collapse under their own gravity. As the cloud contracts, its center heats up until temperatures and pressures become sufficient to ignite nuclear fusion, the process that converts hydrogen into helium while releasing tremendous amounts of energy. For a star much more massive than our Sun, perhaps 20 or 30 times its mass, this hydrogen fusion phase lasts only a few million years rather than the 10 billion years our Sun will enjoy. The massive star burns through its fuel rapidly, because it must maintain higher core temperatures and pressures to support its greater weight against gravitational collapse. When the hydrogen in the core is exhausted, the star doesn't simply die. Instead, it begins fusing helium into heavier elements like carbon and oxygen. This process releases less energy per fusion reaction, so the core must become even hotter and denser to sustain the star. The star then proceeds through a series of fusion stages, creating progressively heavier elements, neon, magnesium, silicon. in nested shells surrounding an increasingly iron-rich core. Each stage happens more quickly than the last, with the final silicon fusion phase lasting only days before the core becomes predominantly iron. Iron represents a critical threshold in stellar nucleosynthesis. Fusing iron into heavier elements doesn't release energy, it consumes energy. Once a massive star's core becomes iron, no further fusion can occur. The core's support against gravity vanishes almost instantly, and it collapses from roughly the size of Earth to perhaps 20 kilometers in diameter in less than a second. This catastrophic implosion creates shock waves that rebound outward through the star's outer layers, heating them to billions of degrees and causing the star to explode with luminosity that can briefly outshine an entire galaxy. For such a sequence to occur within the first billion years of cosmic history requires that star formation began extremely early and proceeded with remarkable efficiency. The universe at that epoch contained very few heavy elements, mostly just hydrogen and helium created in the Big Bang, with trace amounts of lithium. Modern star formation theories suggest that the absence of heavy elements might actually have favoured the formation of more massive stars, since metal-poor gas clouds can collapse more easily into very large concentrations. If confirmed, this would mean the early universe might have been more violent and chemically productive than later epochs, with massive stars living brief, explosive lives that seeded their surroundings with the heavy elements necessary for planets and eventually life. The gamma-ray burst that accompanied this ancient supernova provides additional clues about the explosion's characteristics. Gamma-ray bursts represent the most energetic events in the universe, apart from the Big Bang itself. They occur when a massive star collapses and forms either a black hole or an extremely magnetized neutron star called a magnetar. As matter falls toward the newly formed compact object, it forms an accretion disk and launches powerful jets of particles and radiation along the rotational axis. These jets, moving at nearly the speed of light, produce the intense gamma-ray emission we detect billions of years later when the jet happens to point toward Earth, the darkness that drives everything. While individual discoveries like the record-breaking supernova capture attention and headlines, perhaps the most profound development from recent observations concerns something we cannot see, touch, or directly detect: dark energy. This mysterious component is thought to comprise roughly 68% of all energy in the universe, yet we know almost nothing about what it actually is. For decades, the prevailing model treated dark energy as essentially a cosmological constant, a property of empty space itself that remains fixed and unchanging throughout cosmic time. In 2024, observations from the Dark Energy Spectroscopic Instrument, or DESI, began challenging this comfortable assumption. DESI is a ground-based survey operating on the Mayall telescope in Arizona, designed to measure the distances and velocities of millions of galaxies across vast stretches of cosmic time. Over the course of its observing program, DSI collected data on approximately 6.4 million galaxies and quasars, creating the most detailed three-dimensional map of the universe's large-scale structure ever produced. When researchers analyzed this data alongside measurements from exploding stars called Type 1, or supernovae, which serve as standardized candles for measuring cosmic distances, they found something unexpected. The observations suggested that the relationship between dark energy's density and its pressure might change over time, rather than remaining constant as the standard cosmological model assumes. This is significant because dark energy's behavior directly influences the expansion rate of the universe. If dark energy maintains constant density even as space expands, it acts as an accelerating force that will eventually drive galaxies apart faster than light can travel between them, leading to what cosmologists call the heat death of the universe. But if dark energy's density changes over time, following what physicists call a dynamic equation of state, then the universe's ultimate fate becomes far less certain. The DESI survey works by measuring the redshift of millions of galaxies, essentially determining how fast they're moving away from us due to cosmic expansion. But the survey does more than simply measure individual galaxy velocities. It maps the three-dimensional distribution of matter across enormous volumes of space, revealing patterns called baryon acoustic oscillations, essentially the fossilized imprint of sound waves that propagated through the early universe before atoms formed. These patterns provide a standard ruler for measuring cosmic distances, similar to how Type 1 or supernovae provide standard candles for brightness measurements. By comparing the observed distribution of galaxies with theoretical predictions from different cosmological models, DC researchers can test whether dark energy behaves as a cosmological constant or evolves over time. The 2024 results suggest the latter, though with caveats about statistical significance that we'll explore shortly. If confirmed, this finding would represent one of the most significant discoveries in fundamental physics since Einstein formulated general relativity, potentially requiring new theories about the nature of vacuum energy and the fundamental structure of space-time, the statistical weight of uncertainty. When scientists report findings that challenge established models, understanding their confidence level becomes crucial. The DESI results don't represent absolute proof that dark energy evolves over time. Rather, they indicate that models incorporating time-varying dark energy fit the observational data slightly better than models assuming a cosmological constant. The difference is measurable, but not overwhelming. In statistical terms, the evidence falls short of the gold standard threshold that physicists call 5 sigma significance, which corresponds to odds of less than 1 in 3.5 million of being wrong. This might sound disappointing, as if the discovery is tentative or unreliable, but in cosmology, where we have only one universe to observe and cannot run controlled experiments, evidence accumulates gradually through multiple independent observations that either support or contradict specific models. The DESI results gain significance when, combined with other recent observations suggesting that the expansion rate of the universe appears different when measured in different ways, a tension that has been growing in recent years and remains one of the most pressing puzzles in fundamental physics. Some measurements, based on observations of the cosmic microwave background radiation left over from the Big Bang, suggest the universe is expanding at about 67 kilometers per second per megaparsec. A megaparsec equals roughly 3.26 million light-years, so this means that for every 3.26 million light-years of distance between us and a galaxy, that galaxy appears to be receding at an additional 67 kilometers per second due to cosmic expansion. Other measurements, based on observations of pulsating stars called Cepheid variables, and Type 1 or supernovae in relatively nearby galaxies, suggest an expansion rate closer to 73 kilometers per second per megaparsec. This approximately 9% discrepancy might not sound enormous, but it represents a fundamental disagreement about a basic property of the universe. The possibility that dark energy evolves over time offers one potential resolution to this tension. If dark energy's influence has changed throughout cosmic history, then measurements based on the early universe, like the cosmic microwave background, and measurements based on relatively recent cosmic epochs, like nearby supernova, might naturally yield different values. Confirming this would require rewriting our fundamental understanding of what drives cosmic expansion and potentially revising Einstein's general relativity, the theoretical framework that has successfully described gravity for more than a century. Understanding the statistical significance of these findings requires appreciating the complexity of the analysis. DESY's dataset contains millions of galaxy positions and redshifts, but extracting meaningful cosmological information requires accounting for numerous systematic effects. Dust. Extinction dims distant galaxies unpredictably. Gravitational lensing by foreground matter distorts the apparent positions of background galaxies. The instruments themselves introduce subtle biases that must be carefully calibrated. Each of these effects can potentially mimic or obscure real cosmological signals, so researchers must develop sophisticated analysis techniques that separate genuine patterns from artifacts. The invisible giants of the early universe black holes represent another frontier where recent discoveries have challenged theoretical expectations. The James Webb Space Telescope has confirmed the presence of actively growing supermassive black holes in galaxies that formed just 570 million years after the Big Bang. To appreciate why this matters, consider the growth timescales involved in creating such massive objects. A supermassive black hole, defined as one containing millions or billions of times the Sun's mass, doesn't form instantly. The most straightforward formation mechanism starts with a massive star that explodes as a supernova, leaving behind a stellar mass black hole perhaps 10 to 100 times the Sun's mass. This black hole then grows by accreting matter from its surroundings, gas, dust, and occasionally entire stars that wander too close. The accretion process releases tremendous energy as matter spirals inward, heating to millions of degrees and emitting intense radiation across the electromagnetic spectrum. Here's the problem. There are physical limits to how quickly a black hole can grow through accretion. As matter falls toward the black hole, it heats up and emits radiation. This radiation exerts outward pressure on surrounding matter, potentially pushing it away and limiting how much material can actually reach the black hole. This feedback mechanism is called the Eddington limit, after British astrophysicist Arthur Eddington, who first calculated it. For a black hole to grow from stellar mass to supermassive proportions while respecting the Eddington limit requires hundreds of millions to billions of years. Yet JWST is finding supermassive black holes in galaxies that formed when the universe was only 570 million years old. Not enough time for conventional accretion to produce such massive objects. Several possible explanations exist. Perhaps these black holes formed from the direct collapse of massive gas clouds in the early universe, bypassing the stellar phase entirely and creating what astronomers call seed black holes that were already quite massive to begin with. Or perhaps accretion in the early universe proceeded faster than the Eddington limit would normally allow, driven by exceptionally dense environments or unusual physics we don't yet understand. The detection of these early supermassive black holes challenges not just our understanding of black hole growth, but also our models of galaxy formation. Current theories suggest that supermassive black holes and their host galaxies co-evolve, with the black hole's growth regulated by feedback from the intense radiation it produces. When a black hole accretes matter rapidly, the resulting radiation can heat surrounding gas and drive powerful winds that sweep through the galaxy, temporarily shutting down both star formation and further black hole growth. This feedback mechanism creates a self-regulating system that links black hole mass to galaxy properties. The fact that supermassive black holes existed when galaxies were still very young and small suggests this feedback process might work differently in the early universe. Perhaps the first black holes grew during a brief period before feedback mechanisms became effective. Or perhaps the dense, turbulent conditions in early galaxies allowed black holes to accrete matter through channels that avoided the Eddington limit. For instance, through dense streams of cold gas that could flow directly toward the black hole without forming a hot accretion disk. The architecture of infant galaxies. The discovery of early supermassive black holes connects to a broader mystery about how galaxies themselves assembled in the universe's first billion years. The current model of cosmic structure formation, called lambda cold dark matter, or lambda CDM, describes a universe where dark matter formed the gravitational scaffolding around which normal matter collected to build galaxies. In this framework, structure forms hierarchically. Small dark matter halos merge to create larger ones, and galaxies grow through a combination of mergers and steady accretion of surrounding gas. This model has proven remarkably successful at explaining many features of the cosmos we observe today, from the distribution of galaxy clusters to the patterns in the cosmic microwave background. But JWST observations of the early universe have revealed galaxies that appear surprisingly mature and massive at epochs, when they should still be small and relatively unstructured. Some of these early galaxies show clear evidence of rotation, organized structure, and even the presence of heavy elements that indicate previous generations of stars must have already lived and died to enrich the gas. The galaxy harboring the supermassive black hole detected at 570 million years after the Big Bang, officially designated CANUCS-LRD-Z 8.6, represents part of a class of objects that have puzzled astronomers. These galaxies appear as luminous red dots in JWST's deep images, combining intense brightness with very red colours that indicate they're extremely distant. The redness comes from the Lyman break, a specific feature in the spectrum of hydrogen that gets shifted into longer wavelengths by cosmic expansion. By studying these Lyman break galaxies in detail, astronomers can reconstruct the conditions in the early universe and understand how the first generation of galaxies assembled. What makes CANUCS LRDZ 8.6 particularly significant is the connection it provides between early black holes and the luminous quasars we observe throughout cosmic history. Quasars are among the most energetic objects in the universe, powered by supermassive black holes accreting matter at prodigious rates. The intense radiation from the accretion disk can outshine the entire host galaxy, making quasars visible across vast cosmic distances. Some quasars emit more than 1 trillion times the Sun's luminosity, releasing this energy from a region smaller than our solar system. Astronomers have identified quasars at various cosmic epochs, from relatively nearby ones only a few billion light-years away to extremely distant examples shining when the universe was less than 1 billion years old. The existence of a clear evolutionary sequence connecting the early supermassive black holes detected by JWST to these later quasars suggests that we're witnessing the formation phase of systems that will eventually become the bright quasars visible at later times. Understanding this connection helps explain how black holes and galaxies co-evolved throughout cosmic history. The chemical composition of these early galaxies provides additional clues about their formation history. Spectroscopic observations can identify specific elements present in the gas and stars, revealing which generations of stars have already lived and died. Elements heavier than helium, what astronomers call metals, regardless of their chemical properties, are created in stellar interiors and dispersed through supernovae. The presence of significant metal enrichment in galaxies at very early times suggests that multiple generations of stars must have formed, lived, and died in quick succession during the universe's first few 100 million years. The question of primordial populations. The existence of supermassive black holes in the early universe raises profound questions about whether an entirely different population of stars might have existed in the universe's first few 100 million years. Theoretical astrophysicists have long speculated about population 3 stars, the first generation of stars to form in the universe, composed purely of hydrogen and helium without any heavier elements. These stars, if they existed, would have been fundamentally different from any stars we observe today. Without heavy elements to facilitate cooling in collapsing gas clouds, population 3 stars might have formed with masses hundreds or even thousands of times greater than the Sun. Such massive stars would have burned with extraordinary brightness and lived extremely brief lives, perhaps only a few million years before exploding or collapsing directly into black holes. Some theories suggest these first-generation stars might have had masses sufficient to leave behind black holes of 100 or even 1,000 solar masses, much larger seeds than stellar mass black holes from normal stars. Despite decades of searching, no one has ever definitively observed a population 3 star or even the chemical signature of a region where only population 3 stars have lived and died. The reason relates to their brief lifetimes and the rapid pace of chemical enrichment they would have caused. A single population 3 supernova would have dispersed heavy elements throughout its surrounding region, ensuring that the next generation of stars formed from chemically enriched material. This means population 3 stars might have existed only for a very brief window in cosmic history, perhaps only a few 100 million years, before their own deaths ended the conditions necessary for their formation. The discovery of supermassive black holes at very early times provides indirect evidence that something unusual was happening in the universe's first few 100 million years. Whether this something was population 3 stars, direct collapse black holes, or some other mechanism we haven't yet imagined remains an open question. Future observations with JWST and other instruments may help resolve this mystery by finding galaxies or regions where the chemical signatures suggest only 1 or 2 generations of stars have ever formed. Theoretical models of population 3 stars predict they would have had unusual properties compared to modern stars. Without metals to transport energy from their cores through radiation, these stars would have relied primarily on convection, the physical motion of hot gas rising from the centre and cool gas sinking back down. This would have made their interiors thoroughly mixed, bringing fresh hydrogen to the core and allowing these stars to burn a larger fraction of their total mass than metal-rich stars can. The increased efficiency might have extended their already brief lifetimes, slightly while also affecting the composition of the material they eventually ejected, the distribution of cosmic darkness. The discovery of Gaia BH3 raises intriguing questions about the population of stellar mass black holes in the Milky Way, and potentially in other galaxies. Theoretical models predict that our galaxy should contain tens of millions of stellar mass black holes, the remnants of massive stars that have lived and died over the galaxy's roughly 13 billion year history. Yet we've only confirmed the existence of a few dozen of these objects, mostly in binary systems where the black hole is actively accreting matter from its companion star. The reason for this observational deficit relates to the difficulty of detecting isolated black holes. If a black hole isn't actively consuming nearby matter, or gravitationally influencing a visible companion, it remains essentially invisible, a dark, silent object drifting through space. Gaia's capability to detect orbital wobbles in stars represents one of the few techniques available for finding these otherwise invisible objects, and the satellite's data catalogue likely contains evidence of many more black holes waiting to be discovered through careful analysis. What makes Gaia BH3 particularly interesting isn't just its mass, but what that mass implies about the star that created it. For a stellar remnant to be so massive, the progenitor star must have been exceptionally large, perhaps 80 or 100 solar masses or even more. Stars this massive are quite rare, comprising only a tiny fraction of stellar populations. They also live very brief lives, exhausting their nuclear fuel in only a few million years compared to the billions of years that Sun-like stars enjoy. The existence of such a massive black hole relatively nearby, Gaia BH3 lies only about 2,000 light-years from Earth, suggests that the local stellar neighbourhood has seen the formation and death of very massive stars more recently than we might have expected. It also provides a crucial data point for understanding how massive stars end their lives. Do stars in this mass range always collapse into black holes, or do some explode as pair instability supernovae, obliterating themselves completely without leaving any remnant? The discovery of Gaia BH3 confirms that at least some stars in this mass range do leave behind black hole remnants, but whether this is the universal outcome remains unknown. Pair instability supernovae represent a particularly interesting class of stellar explosions predicted by theory but not yet definitively observed. When a star becomes massive enough and hot enough in its core, gamma-ray photons can spontaneously transform into electron-positron pairs, a process that removes energy from the core and reduces the pressure supporting the star against gravity. This can trigger runaway collapse followed by explosive oxygen burning that produces so much energy the entire star is blown apart, leaving no remnant whatsoever. Theory suggests this should happen in stars with cores between roughly 60 and 130 solar masses but observations of such events remain uncertain and controversial. The silence between the stars. Another category of black hole discoveries has emerged in recent years: the detection of so-called wandering or runaway black holes that have been ejected from their host galaxies and now travel through intergalactic space. In early 2025, JWST confirmed the first clear case of such an object, a supermassive black hole with a mass equivalent to millions of suns rocketing through its home galaxy at approximately 2.2 million miles per hour, or about 3.5 million kilometers per hour. This extraordinary velocity poses an immediate question: what could possibly accelerate something so massive to such tremendous speeds? The answer likely lies in gravitational wave recoil, a prediction of Einstein's general relativity that wasn't confirmed until recently. When two supermassive black holes merge, they release tremendous amounts of energy in the form of gravitational waves, ripples in spacetime itself that propagate outward at the speed of light. If the merger isn't perfectly symmetric, more gravitational waves are emitted in one direction than another, creating a net momentum that kicks the merged black hole in the opposite direction. The physics here parallels the recoil of a rifle when it fires a bullet. The bullet carries momentum in one direction, so conservation of momentum requires the rifle to move in the opposite direction. With black hole mergers, the asymmetric emission of gravitational waves plays the role of the bullet, and the merged black hole experiences the recoil. Depending on the masses of the merging black holes and the orientation of their spins, this recoil can reach thousands of kilometers per second, sufficient to eject even a supermassive black hole from its host galaxy. The asymmetry necessary for significant recoil can arise in several ways. If the two merging black holes have very different masses, the emission pattern naturally becomes asymmetric. More importantly, if the black holes are spinning and their spin axes point in different directions. The complex dynamics of the merger can produce strong asymmetric gravitational wave emission. The maximum recoil velocity depends on the specific configuration, but theoretical calculations suggest kicks of up to 5,000 km per second are possible under optimal conditions, fast enough to escape even the most massive galaxy clusters. The runaway black hole detected by JWST provides observational confirmation that these violent recoil events actually occur in nature, and not just in theoretical calculations and computer simulations. The black hole's velocity of roughly 3.5 million kilometers per hour translates to about 1,000 kilometers per second. Substantial, but not at the theoretical maximum, suggesting a moderately asymmetric merger rather than the most extreme possible configuration. The cosmic fossil record. The runaway black hole detected by JWST leaves behind a visible trail as it plows through the intergalactic medium, compressing and heating the diffuse gas in its path. This trail extends for approximately 200,000 light-years behind the black hole, appearing as a faint streak in JWST's observations. The presence of this trail provides crucial evidence that the black hole is indeed moving at high velocity and not simply sitting quietly in an unusual location. Observations like this open a new window into understanding galaxy mergers and the dynamics of supermassive black holes. When two galaxies collide and merge, their central black holes eventually sink toward the center of the merged system and form a binary pair. These black hole binaries gradually spiral inward, losing energy to gravitational wave emission, until they finally merge in a catastrophic event that can briefly release more power than all the stars in the observable universe combined, until recently we could only infer these merger events from theory and from observations of galaxy pairs at various stages of interaction. The detection of gravitational waves by LIGO and other instruments has confirmed that stellar mass black holes do indeed merge, producing measurable spacetime ripples. But supermassive black hole mergers produce gravitational waves at frequencies too low for ground-based detectors to measure. Future space-based gravitational wave observatories like LISA, scheduled to launch in the 2030s, will be able to detect these events directly. The discovery of runaway black holes ejected by merger recoil provides an independent confirmation that supermassive black hole mergers do occur and that they release energy asymmetrically as general relativity predicts. Each ejected black hole represents a fossil record of a violent merger event billions of years in the past. By studying these objects and their trajectories, astronomers can reconstruct the merger history of galaxies and understand how supermassive black holes grow through a combination of accretion and mergers. The trail of compressed gas behind the runaway black hole also provides information about the density and distribution of intergalactic gas, material that exists between galaxies rather than within them. This intergalactic medium contains roughly half of all the ordinary matter in the universe, yet remains difficult to study because it's so diffuse and emits very little light. The glowing trail created by the runaway black hole essentially traces out a path through this otherwise invisible material, revealing its properties in unprecedented detail. The nearest stellar neighbours. While some discoveries probe the farthest reaches of space and time, others have occurred remarkably close to home. In 2024, astronomers announced compelling evidence for an exoplanet orbiting Barnard's star, a red dwarf located just 6 light-years from Earth. This makes Barnard's star the second closest stellar system to our Sun, surpassed only by the Alpha Centauri triple star system at roughly 4.4 light-years. The newly discovered planet, at least half the mass of Venus, completes an orbit around Barnard's star every 3.15 Earth days. This extremely short orbital period means the planet orbits very close to its star, much closer than Mercury orbits our Sun. Despite this proximity, the planet doesn't necessarily experience scorching temperatures because Barnard's star is a red dwarf, much cooler and dimmer than our Sun. Red dwarfs emit most of their energy in infrared wavelengths, and their habitable zones, the regions where liquid water could exist, on a planet's surface, lie much closer to the star than Earth's orbit lies to the Sun. The detection technique used to find this planet involves measuring the star's radial velocity, how quickly it moves toward or away from us, using the Doppler effect. As a planet orbits its star, the gravitational tug between them causes the star to wobble slightly. When the star moves toward Earth, the light we receive is shifted slightly towards shorter wavelengths, blue shift. When it moves away, the light shifts toward longer wavelengths, red shift. By measuring these tiny shifts in the star's spectrum over many nights of observation, astronomers can infer the presence of planets and determine their minimum masses and orbital periods. Barnard's star has a complicated history of planetary claims. In the 1960s and 1970s, astrometric observations suggested the presence of 1 or possibly 2 planets orbiting the star. These claims generated considerable excitement but eventually couldn't be confirmed with improved observations. For decades, Barnard's star stood as a cautionary tale about the difficulty of detecting exoplanets and the importance of rigorous verification. The 2024 detection uses modern, highly sensitive spectrographs that can measure radial velocity variations of less than 1 meter per second, comparable to a leisurely walking pace, and represents a far more reliable detection than the earlier astrometric claims. The observations were conducted using the espresso spectrograph on the European Southern Observatory's Very Large Telescope in Chile. Espresso achieves its remarkable precision through a combination of advanced technology, including laser frequency combs for wavelength calibration and careful control of instrumental temperature and pressure. The instrument observes starlight through multiple exposures over many nights, building up a data set that reveals the periodic velocity variations caused by an orbiting planet while averaging out random, noise and instrumental effects, the architecture of nearby worlds. The discovery at Barnard's star gained significance from the star's proximity and its characteristics as a red dwarf. Red dwarfs are the most common type of star in our galaxy, comprising roughly 70 to 75% of all stars. They're also remarkably long-lived, a red dwarf can burn hydrogen in its core for trillions of years, far longer than the current age of the universe. This longevity means that red dwarf systems represent stable environments where, in principle, life might have billions of years to emerge and evolve. However, red dwarfs also present challenges for habitability. Many red dwarfs, especially young ones, experience intense magnetic activity and produce frequent stellar flares, sudden eruptions that release tremendous amounts of high-energy radiation and charged particles. A planet in the habitable zone of a red dwarf orbits close enough that it would be bathed in this radiation during flare events, potentially stripping away any atmosphere and sterilizing the surface. Whether planets around red dwarfs can maintain habitable conditions remains one of the key questions in exoplanet science. The planet discovered around Barnard's star orbits too close to be in the habitable zone, but the detection hints at the possibility of additional planets farther out. The observations also indicated potential signatures of 3 more planetary candidates in the system, though these remain unconfirmed pending additional data. If confirmed, Barnard's star would join a growing list of nearby red dwarfs hosting multiple planets, suggesting that planetary systems around these small, cool stars might be just as common and complex as systems around Sun-like stars. The proximity of Barnard's star makes it an attractive target for future direct imaging observations. While the newly discovered planet orbits too close to be separated from the star's glare, any planets farther out in the habitable zone might eventually be detectable. With next-generation instruments, the extremely large telescope, currently under construction in Chile with a primary mirror 39 meters in diameter, will have the light-collecting power and angular resolution to potentially image planets around Barnard's star directly, revealing details about their atmospheres and surface conditions. Red dwarf planets also interest astronomers because they provide natural laboratories for studying atmospheric escape, the process by which planets lose their atmospheres to space. Because habitable zone planets orbit close to red dwarfs, they're subjected to intense ultraviolet radiation and stellar wind. This high-energy environment should drive rapid atmospheric loss, particularly for smaller planets without strong magnetic fields. Observing how much atmosphere red dwarf planets retain over time helps us understand which planetary characteristics allow atmospheres to persist and which lead to rapid loss and desiccation. The red surface of ancient rocks. Returning to our own solar system, 2025 brought a tantalizing discovery on Mars that might represent the most compelling evidence yet for ancient life on another world. NASA's Perseverance rover, exploring Jezero crater near the Martian equator, encountered a rock displaying unusual features that on Earth would be considered strong biosignatures. The rock shows distinctive patterns described as leopard spots, light red circular features ringed by darker material and laced with iron phosphate compounds. On Earth, similar leopard spot patterns form through 2 known mechanisms. The first involves exposure to extremely hot acidic conditions that alter the rock's chemistry and create color variations as different minerals form and oxidize. The second mechanism involves biological activity, where microorganisms use chemicals in the rock as energy sources and leave behind distinctive patterns of mineral deposits as waste products. The key insight is that the hot acidic conditions necessary for abiotic formation of these patterns haven't existed in Jezero crater for billions of years, making biological formation the more plausible explanation given the rock's age and context. The rover's instruments also detected organic molecules within clay sediments in the same rock. Organic molecules contain carbon-hydrogen bonds and can form through either biological or non-biological processes, so their presence alone doesn't prove life existed. However, the combination of organic molecules and leopard spot patterns in the same rock sample strengthens the case for biological origin. Perseverance's instruments weren't able to identify the specific organic molecules present, which would have provided additional clues about their origin, but the detection itself represents significant evidence. Perseverance carries a sophisticated suite of instruments for studying Martian rocks. The Pixel instrument uses X-ray fluorescence to map the elemental composition of rock surfaces with sub-millimeter precision, revealing variations in iron, calcium, sulfur, and other elements that indicate different minerals. The Sherlock instrument uses ultraviolet Raman spectroscopy and fluorescence to detect organic molecules and map mineral distributions. Together, these instruments can create detailed chemical and mineralogical maps of rock surfaces, revealing patterns that would be invisible to cameras alone. The leopard spots in the Martian rock show precisely the kind of chemical and mineralogical patterns that Pixel and Sherlock were designed to detect. The light-coloured spots contain higher concentrations of iron and phosphate than the surrounding rock, while the dark rings contain different minerals enriched in other elements. On Earth, when chemosynthetic bacteria oxidize iron compounds to extract energy, they often deposit the oxidized iron in distinctive patterns around their colonies, creating structures remarkably similar to what Perseverance observed, the patience of astrobiology. It's crucial to understand that this Martian discovery doesn't constitute proof of past life. Rather, it represents what astrobiologists call a compelling biosignature worthy of further investigation. The difference is subtle but important. Proof would require either finding fossilized microorganisms, detecting complex organic molecules that could only have formed biologically, or observing some other unambiguous signature that no non-biological process could create. The leopard spots and organic molecules meet a lower threshold. They're consistent with biology, and difficult to explain otherwise, but not impossible to explain without invoking life. The ultimate resolution will likely require returning samples from Mars to Earth for detailed laboratory analysis. Perseverance is collecting and caching samples from Jezero crater, storing them in sealed tubes that a future mission could retrieve and bring back to Earth. Once in terrestrial laboratories, these samples could be analysed with instruments far more sophisticated than what can be sent to Mars, potentially revealing definitive evidence one way or another about ancient Martian life. Jezero crater was chosen as Perseverance's landing site precisely because orbital observations indicated it once held a lake fed by rivers flowing down from the crater rim. The lake existed roughly 3.5 billion years ago, during Mars' Noachian period when the planet had a thicker atmosphere and more temperate conditions than today's frozen desert world. If life ever arose on Mars, it likely did so during this ancient epoch, when liquid water was stable on the surface and the environment might have resembled early Earth. The rocks Perseverance is studying formed in this ancient lake environment, accumulating sediments and potentially preserving evidence of whatever microbial life might have existed. The discovery of leopard spots in such rocks suggests that if Martian microbes did exist, they might have been similar in some ways to certain Earth bacteria that derive energy from chemical reactions rather than sunlight. These chemosynthetic organisms use minerals as energy sources, oxidizing iron or sulfur compounds, and leaving behind distinctive mineral deposits as waste products. Mars sample return represents one of the highest priorities in planetary science, but also one of the most complex and expensive missions ever attempted. The plan involves launching a spacecraft to Mars that will locate and collect the sample tubes cached by Perseverance, load them into a small rocket called a Mars Ascent Vehicle, launch that rocket from the Martian surface into orbit, rendezvous with an Earth return vehicle, and finally return the samples to Earth where they'll be quarantined and studied in specialized laboratories. The entire process will likely take more than a decade and cost billions of dollars, but the potential scientific return, definitively answering whether life ever existed beyond Earth, makes the investment worthwhile. The convection of distant atmospheres. Moving beyond Mars to more distant worlds, 2025 brought surprising observations of Titan, Saturn's largest moon, and the only moon in our solar system with a substantial atmosphere. Scientists combining data from JWST and the Keck 2 telescope in Hawaii reported the first evidence of atmospheric convection, rising columns of warm gas, in Titan's northern hemisphere. This might sound mundane, but it represents a significant finding for understanding weather and climate on this enigmatic world. Titan has long fascinated planetary scientists because it's the only place besides Earth known to have stable liquid on its surface. However, this liquid isn't water but hydrocarbons, primarily methane and ethane, that form lakes and seas in Titan's polar regions. The Moon's surface temperature hovers around -179 degrees Celsius or -290 degrees Fahrenheit, cold enough that methane and ethane exist as liquids while water is frozen as hard as rock. The detection of atmospheric convection in the northern hemisphere, where most of Titan's lakes are located, suggest active weather processes that likely include methane rain. On Earth, convection drives weather when warm, moist air rises, cools, and releases its moisture as precipitation. On Titan, the process appears similar but involves methane vapor instead of water vapor. Warm pockets of atmosphere enriched in methane gas rise toward higher altitudes, cool, and potentially condense into clouds that rain liquid methane back to the surface, replenishing the lakes and seas. The observations required combining data from two very different instruments. JWST observed Titan in infrared wavelengths, particularly sensitive to methane emission from the atmosphere. By measuring how much infrared light comes from different altitudes and locations, astronomers can map temperature variations and identify regions where warm gas is rising. The Keck telescope, equipped with adaptive optics to compensate for atmospheric blurring, provided complementary observations at slightly different wavelengths, confirming the convective features and providing additional constraints on their altitude and extent. Detecting convection on Titan required patient observation and careful analysis. The convective cells, regions of rising warm gas, appear and disappear over timescales of hours to days, so multiple observations spread across weeks were necessary to confirm that the features were real and not instrumental artifacts. The fact that both JWST and Keck independently detected similar patterns at the same times and locations provides strong evidence that genuine atmospheric dynamics are occurring. The seasons of a distant world Titan experiences seasons because Saturn's axis is tilted relative to its orbit around the Sun, much like Earth's axial tilt causes our seasons. However, Titan's seasonal cycle lasts about 29.5 Earth years, the time Saturn takes to complete one orbit. The Moon had been experiencing northern winter when the Cassini spacecraft studied it extensively from 2004 to 2017, with the northern summer solstice occurring in 2017 shortly after Cassini's mission ended. The new observations of convection in the northern hemisphere, made in 2025, come during Titan's northern spring as summer approaches. The timing suggests that seasonal warming of the northern polar region might be driving increased evaporation from the lakes, enriching the local atmosphere with methane vapor and creating conditions favorable for convection. If this interpretation is correct, the coming years should see increased cloud activity and rainfall in Titan's north, which future observations could potentially confirm. Understanding Titan's atmospheric dynamics has implications beyond just this one moon. Titan represents a kind of natural laboratory for studying atmospheric chemistry and climate on a world very different from Earth, yet governed by the same physical principles. The Moon's thick nitrogen atmosphere undergoes complex photochemistry driven by solar ultraviolet radiation, creating organic compounds that rain down onto the surface and form the dunes, plains, and lake deposits that spacecraft have observed. Some scientists speculate that Titan might harbour life despite its frigid temperatures, with organisms that use liquid methane as a solvent instead of water, and derive energy from chemical reactions involving the organic compounds created in the atmosphere. This remains highly speculative, but the discovery of convection and active weather supports the view of Titan as a dynamic, evolving world where complex chemistry occurs and where, in principle, some form of exotic biochemistry might be possible. Titan's methane cycle parallels Earth's water cycle in fascinating ways. Methane evaporates from lakes and seas, rises into the atmosphere, forms clouds, and precipitates as rain. Over geological time, Methane should be destroyed by photochemical reactions in the upper atmosphere, converted into more complex hydrocarbons that drift down as haze and eventually accumulate on the surface. The fact that Titan's atmosphere remains rich in methane suggests some process must be replenishing it. Either ongoing volcanic or cryovolcanic activity releasing methane from the interior, or chemical recycling that converts surface hydrocarbons back into methane. The interior structure of ice worlds. Another surprising finding about Titan emerged from reanalysis of data collected by the Cassini spacecraft before it ended its mission in 2017. For years, scientists believed that beneath Titan's frozen water ice crust lay a global ocean of liquid water, similar to what's suspected to exist beneath the icy surfaces of Jupiter's moon Europa and Saturn's moon Enceladus. However, new analysis published in late 2025 suggests something very different. A thick, slushy interior composed of a mixture of water ice and liquid that never quite becomes a true ocean. This finding comes from studying how Titan's shape responds to Saturn's gravity. As Titan orbits Saturn, the planet's gravity deforms the moon, creating tidal bulges that rise and fall. The magnitude of these bulges depends on Titan's interior structure. A liquid ocean would allow more deformation than a solid interior, while a slushy mixture would produce an intermediate response. By carefully analyzing Cassini's measurements of Titan's shape changes over time, researchers reconstructed what the interior must be like to produce the observed deformation. The thick, slushy layer, if confirmed, would have significant implications for the possibility of life. A global liquid water ocean provides an environment where, in principle, aquatic microorganisms similar to those in Earth's oceans might exist. A thick slush, however, would be much less hospitable, still containing liquid water but mixed with ice crystals in a way that might make it difficult for biological processes to occur. The finding also affects our understanding of how icy moons evolve over time, and what their internal heat sources might be. The reanalysis technique involved creating detailed computer models of Titan's interior structure and testing how each model would respond to tidal forces. The models vary parameters like the thickness of the ice shell, the amount of ammonia or other antifreezes dissolved in the liquid water, the internal temperature profile, and the size and state of the rocky core. By comparing the predicted tidal response from each model with Cassini's actual observations, researchers can rule out models that don't match and identify which structures are most consistent with the data. This approach has been applied to other icy moons as well, revealing a surprising diversity of internal structures. Europa appears to have a relatively thin ice shell over a deep liquid ocean. Enceladus has a global ocean beneath its south polar region, where geysers erupt through the ice. Ganymede, Jupiter's largest moon, might have multiple layers of ice and liquid water stacked like an onion, with high-pressure ice phases existing deep in the interior. Each moon's structure reflects its unique thermal history and the balance between tidal heating, radioactive decay in the rocky core, and heat loss to space. The awakening of a distant galaxy. One of the most unusual discoveries from recent years involves a galaxy that suddenly started shining much brighter than it ever had before. In late 2019, the previously unremarkable galaxy designated SDSS 1335+0728 began increasing in brightness across all wavelengths, from X-rays to infrared. By 2024, when astronomers had gathered enough data to analyze the phenomenon thoroughly, it became clear that this likely represents the first time we've observed a supermassive black hole waking up at the center of a galaxy. Most galaxies contain supermassive black holes in their centers, but these black holes spend most of their time dormant, not actively consuming significant amounts of matter, and therefore producing little or no radiation. Occasionally, a new supply of gas falls toward the black hole, perhaps triggered by a galaxy merger or the disruption of a passing star. When this happens, the black hole transitions from dormancy to activity, heating, the infalling material to millions of degrees and producing intense radiation across the electromagnetic spectrum. What makes SDSS 1335 plus 0728 special is that astronomers caught this transition happening in real time. Previous observations going back decades show the galaxy looking completely normal, with no signs of an active galactic nucleus. The brightening began in 2019 and has continued since, allowing researchers to track how the black hole's activity level changes over time. This provides unprecedented insight into how active galactic nuclei turn on and evolve during their early stages. The observations require data from multiple telescopes observing at different wavelengths. X-ray observations from space-based telescopes show the high-energy emission from extremely hot gas near the black hole. Optical and ultraviolet observations from ground-based and space-based telescopes reveal emission from slightly cooler material farther out. Infrared observations detect thermal emission from dust heated by the intense radiation. By combining all these observations, astronomers can construct a comprehensive picture of what's happening around the black hole. The leading explanation for what triggered this awakening involves a large cloud of gas falling toward the galactic center. As the gas enters the black hole's gravitational influence, it forms an accretion disk, a flattened, rotating structure where material gradually spirals inward. Friction within the disk heats the gas to tremendous temperatures, causing it to radiate energy. The process can take years to develop fully, which explains why the galaxy has been brightening gradually rather than turning on instantly. The ancient echo of stellar birth. In 2024, the European Southern Observatory announced the completion of a gigantic infrared survey of the Milky Way's central regions, containing more than 1.5 billion astronomical objects. The survey, conducted over 13 years using the Vista telescope in Chile, represents the largest observational project ever carried out with an ESO telescope, generating more than 500 terabytes of data. This infrared map reveals regions of the galaxy invisible to optical telescopes because dust blocks visible light. Infrared radiation penetrates dust clouds more easily, allowing astronomers to peer into star-forming regions, observe stars hidden by obscuring material, and trace the distribution of old stellar populations in the galactic bulge. The sheer number of objects catalogued, 1.5 billion, provides an unprecedented census of the galaxy's stellar content in its central regions. Among the many discoveries enabled by this survey, one particularly interesting finding involves the identification of extremely old stars in the galactic halo and bulge that appear to have formed very early in the Milky Way's history. These ancient stars, visible in infrared but often too cool and dim to detect easily at optical wavelengths, preserve information about the conditions that existed when the galaxy was young. Their chemical compositions reflect the material available at that early time, before generations of massive stars had enriched the interstellar medium with heavy elements. The survey also reveals the three-dimensional structure of the galactic bulge, the central, roughly spherical concentration of stars that makes up a significant fraction of the Milky Way's stellar mass. By measuring distances to millions of stars using their infrared brightness and parallax, astronomers can map out how stars are distributed in the bulge and how they move. This reveals that the bulge has a complex structure with multiple stellar populations of different ages, and compositions suggesting it formed through a combination of processes, including the merging of smaller galaxies early in the Milky Way's history. Understanding the Milky Way's structure and history provides crucial context for interpreting observations of distant galaxies. Every galaxy we observe externally we see as a single integrated system where individual stars can't be resolved. The Milky Way provides the only opportunity to study a galaxy's structure, star by star, measuring individual stellar properties and understanding how different populations contribute to the overall appearance. Insights gained from studying our own galaxy inform our interpretation of distant galaxies, observed with JWST and other telescopes. The neutron star, that almost wasn't another significant discovery from 2024, involves the detection of a neutron star in the remnant of supernova, 1987A, the closest supernova observed in modern times, occurring in the Large Magellanic Cloud satellite galaxy just 168,000 light-years from Earth. Despite being the most studied supernova in history, with observations spanning from visible light to X-rays to radio waves, the nature of the compact object left behind by the explosion remained uncertain for nearly 4 decades. JWST observations provided the crucial evidence by detecting infrared emission consistent with highly ionized gas heated by a central source of high-energy photons. The ionization patterns indicated that only a neutron star, the collapsed core of the original massive star, could produce sufficient high-energy radiation to create the observed emission. This confirmed theoretical predictions that the supernova should have left behind a neutron star rather than a black hole, but the confirmation took almost 40 years because the dense surrounding ejecta obscured the central object from direct observation. Neutron stars represent one of the most extreme states of matter in the universe. When a massive star's core collapses during a supernova, protons and electrons are crushed together to form neutrons, creating an object roughly 20 kilometers in diameter, but containing more mass than the Sun. The resulting density is comparable to atomic nuclei. A teaspoonful of neutron star material would weigh billions of tons if brought to Earth. The physics governing matter at such extreme densities remains poorly understood, because we can't recreate these conditions in laboratories. The detection of the neutron star in SN 1987A provides crucial information for testing theories about neutron star formation and properties. The supernova's progenitor star mass was well constrained from pre-explosion observations, allowing scientists to predict what kind of remnant should form. The confirmation that a neutron star did form, rather than the core collapsing directly to a black hole, validates theoretical models and helps constrain the range of progenitor masses that produce each type of remnant. Neutron stars often manifest as pulsars, rapidly rotating neutron stars that emit beams of radiation from their magnetic poles like cosmic lighthouses. As the neutron star rotates, these beams sweep across space, and if Earth happens to lie in the path of one beam, we detect regular pulses of radiation with precise timing determined by the rotation period. However, not all neutron stars are pulsars, and the neutron star in SN 1987A hasn't been detected as a pulsar despite searches. This might indicate that the beams don't point toward Earth, or that the neutron star's magnetic field has an unusual geometry that doesn't produce strong beamed emission, the bubbles of galactic violence. Moving from individual stellar deaths to the collective impact of many explosions, recent observations have revealed the structure of superbubbles, vast cavities carved into the interstellar medium by generations of supernovae. These features, spanning hundreds of light-years, represent regions where massive star formation has produced not just one supernova, but dozens or hundreds over a span of millions of years. Each explosion adds energy to the expanding bubble, pushing gas outward and creating shells of compressed material where new stars might eventually form. The study of superbubbles helps astronomers understand how energy from stars redistributes matter throughout galaxies and regulates the pace of star formation. When a massive star explodes, it doesn't just enrich the surrounding gas with heavy elements, it also heats that gas to millions of degrees and drives shock waves that can either compress gas and trigger new star formation, or disperse it entirely and shut down star formation for millions of years. The balance between these processes determines whether a galaxy forms stars steadily over billions of years, or experiences bursts of intense formation followed by quiescent periods. JWST and ground-based telescopes have observed superbubbles in nearby galaxies with unprecedented detail, revealing the complex structure of the shells and the distribution of different elements within them. Some regions show strong emission from ionized oxygen and nitrogen, indicating material that was processed through stellar interiors and ejected. Other regions display emission from shocked molecular hydrogen, revealing where the expanding bubble encounters denser clouds of gas. By studying these patterns, astronomers can reconstruct the history of star formation, an explosion that created each superbubble. The Milky Way contains numerous superbubbles, though they're harder to study because we observe them from within the galactic disk rather than from outside. The local bubble, a cavity about 1,000 light-years across surrounding our solar system, represents one such feature created by supernovae that exploded within the last 10 to 20 million years. The Sun currently lies near the edge of this bubble, in a region where the hot interior gas meets the cooler, denser gas of the galactic disk. Understanding superbubbles connects to broader questions about galactic-scale winds and outflows. In galaxies experiencing intense star formation, the collective effect of many supernovae can drive material completely out of the galaxy, creating a galactic wind that carries both energy and chemically enriched gas into the intergalactic medium. This process represents one mechanism by which heavy elements created in stellar interiors can be distributed beyond their host galaxies, potentially enriching the gas from which future galaxies will form. The symphony of stellar surfaces. One of the most visually remarkable discoveries from 2024 involves the first detailed observations of convection cells on the surface of a star other than the Sun. Using the Atacama Large Millimeter/Submillimeter Array in Chile, astronomers captured images of the red supergiant star R Doradus, showing giant bubbles of hot gas rising from the interior, reaching the surface, cooling, and sinking back down. Each bubble spans roughly 75 times the diameter of our Sun, representing convection on a scale impossible in smaller stars. This observation opens a new window into understanding how energy moves through stellar interiors. In the Sun, convection occurs in the outer third of the interior, creating the granulation pattern visible on the solar surface, where each granule represents a small convection cell. But in red supergiant stars, which have much larger sizes and cooler surfaces, convection can dominate the entire envelope, creating enormous cells that overturn on timescales of months to years rather than the minutes to hours typical of solar granulation. R Doradus, located about 180 light-years from Earth, represents a late stage in stellar evolution when a Sun-like star has exhausted its core hydrogen, expanded to enormous size, and cooled to a surface temperature around 3000 Kelvin, cool enough that molecules can form in its atmosphere. The star pulsates irregularly as convective cells rise and fall, causing its brightness to vary in complex patterns. By observing these brightness variations and correlating them with the spatial structure revealed in ALMA images, astronomers can test theoretical models of convection and pulsation in evolved stars. The achievement represents a technical tour de force. R Doradus appears only about 0.06 arcseconds across as seen from Earth, roughly equivalent to resolving a quarter at a distance of 50 kilometers. ALMA achieved this resolution by combining signals from dozens of antennas spread across the high desert of northern Chile, using interferometric techniques that synthesize an effective telescope aperture 16 kilometers in diameter. The data processing required correlating signals from all antenna pairs and carefully calibrating instrumental and atmospheric effects to produce a coherent image. Similar observations of other red supergiants and evolved stars will help astronomers understand how these massive stars lose mass during their final evolutionary phases. Red supergiants can shed substantial fractions of their total mass through steady stellar winds and episodic ejections, fundamentally altering their structure and determining whether they end their lives as supernova or collapse directly to black holes. The convection patterns visible on their surfaces likely play a crucial role in driving mass loss, perhaps by lifting material to altitudes where radiation pressure can accelerate it outward, the unexpected behavior of solar storms. The May 2024 solar storm that collapsed Earth's plasmasphere revealed another unexpected feature. The solar wind that caused the disturbance had unusual properties that don't fit standard models of how the Sun produces this outflow. Traditional understanding suggests that fast solar wind originates from coronal holes, regions where the Sun's magnetic field lines extend outward into space rather than looping back to the surface. Slow solar wind comes from other regions where field lines do loop back, but material still manages to escape. However, observations from the European Space Agency's Solar Orbiter spacecraft during and after the May 2024 storm showed a more complex picture. The spacecraft measured solar wind that seemed to transition between fast and slow states in ways that couldn't be explained by simply crossing between coronal holes and other regions. Instead, the data suggested that the solar wind's speed and properties can change due to dynamic processes occurring in the corona itself, perhaps wave activity or small-scale reconnection events that episodically accelerate particles. This discovery helps resolve a decades-old mystery about solar wind origins. Previous spacecraft observed the solar wind at Earth's distance, but couldn't definitively connect that wind back to specific regions on the Sun's surface. Solar Orbiter's closer approach, venturing inside Mercury's orbit, combined with coordinated observations from other spacecraft and ground-based solar telescopes, allowed researchers to make these connections for the first time. The results showed that our simple picture of fast wind from coronal holes and slow wind from elsewhere misses important complexity. Understanding solar wind generation matters for practical reasons. The solar wind shapes Earth's magnetosphere and drives space weather events that can affect satellites, power grids, and communication systems. More accurate models of how the Sun produces variable solar wind will improve our ability to predict when Earth might encounter high-speed streams or particularly dense solar wind that could trigger geomagnetic storms. These predictions become increasingly important as our technological infrastructure grows more sophisticated and more vulnerable to space weather effects. The May 2024 storm also provided opportunities to study how Earth's upper atmosphere responds to intense solar forcing. Satellites measuring atmospheric density and composition detected substantial heating and expansion of the thermosphere, the atmospheric layer where most satellites orbit. This expansion increases drag on satellites, accelerating their orbital decay and requiring more frequent adjustments to maintain proper altitude. During intense storms, low-orbiting satellites can lose significant altitude in just hours, and in extreme cases might even re-enter the atmosphere prematurely if operators can't raise their orbits quickly enough. The forest of cosmic filaments. Beyond individual discoveries about specific objects, one of the broader revelations from the DEEI survey involves the detailed mapping of cosmic large-scale structure, the intricate web of filaments, sheets and voids that characterize matter distribution on the larger scales. By measuring positions and redshifts for millions of galaxies, DESI has created three-dimensional maps showing how this structure evolved over the past 11 billion years of cosmic history. The maps reveal that the cosmic web has been remarkably stable in its overall characteristics, even as individual structures have grown through gravitational attraction. Filaments that existed when the universe was only a few billion years old have persisted and grown denser, accreting more galaxies and gas over time. The voids between filaments have expanded as cosmic expansion continues, but haven't fundamentally changed their topology. This stability suggests that the initial conditions, established during the universe's first few 100,000 years, imprinted as tiny density fluctuations in the cosmic microwave background, have successfully predicted the large-scale structure we observe billions of years later. However, the detailed structure shows subtle deviations from the simplest predictions. Some regions appear to have grown denser faster than models suggest, while others lag behind. These discrepancies might indicate that our understanding of dark matter or dark energy requires refinement, or they might simply reflect statistical fluctuations. It's difficult to know with certainty when we have only one universe to observe. Ongoing analysis of DESI data aims to quantify these anomalies and determine whether they point toward new physics or remain within the range of expected variation. The cosmic web's filamentary structure arises from gravitational instability, acting on the nearly uniform matter distribution present shortly after the Big Bang. Regions slightly denser than average attracted more matter, growing denser still and attracting matter even more strongly. This runaway process caused matter to collapse primarily in 2 dimensions, forming sheets, which then collapsed in 1 dimension to form filaments. Where filaments intersect, galaxy clusters formed, the most massive gravitationally bound structures in the universe, containing hundreds or thousands of galaxies along with vast amounts of hot gas. By studying how galaxies populate different environments within the cosmic web, whether they sit in dense cluster cores, along filaments, in sheets or in voids, astronomers can understand how environment influences galaxy evolution. Galaxies in dense clusters experience frequent interactions and mergers, triggering bursts of star formation or, conversely, stripping away their gas and quenching star formation. Galaxies in voids, isolated from neighbours, evolve more peacefully with steadier star formation rates. The DESI survey's comprehensive catalogue allows statistical studies of these environmental effects across cosmic time. The rotation of stellar corpses, another window into stellar physics, comes from studying neutron stars' rotation rates and how they change over time. Pulsars, rapidly rotating neutron stars that emit beams of radiation, provide natural laboratories for testing physics at extreme densities. Their rotation periods range from milliseconds to seconds, and these periods gradually lengthen as the neutron stars lose rotational energy through electromagnetic radiation and particle outflows. Recent pulsar timing campaigns using radio telescopes around the world have achieved unprecedented precision in measuring these rotation periods and their changes. Some measurements track pulsar periods to better than a nanosecond, a billionth of a second, allowing detection of incredibly subtle changes in rotation rate. This precision reveals that neutron star interiors must have complex structure, possibly including superfluid components that can decouple from the solid crust and rotate at different rates. Occasionally, pulsars experience sudden spin-ups called glitches, where the rotation period abruptly decreases by a tiny amount before resuming its gradual slowdown. These glitches likely occur when superfluid vortices in the neutron star interior suddenly transfer angular momentum to the crust, causing a brief speed-up. By studying the frequency, magnitude and recovery behavior of glitches, physicists can constrain models of neutron star internal structure and the properties of matter at nuclear densities, conditions impossible to reproduce in laboratories. The fastest spinning pulsars, called millisecond pulsars, complete hundreds of rotations per second. These extreme rotation rates arise through a process called recycling, where a neutron star in a binary system accretes matter from its companion star. The infalling matter carries angular momentum that spins up the neutron star, eventually reaching rotation periods as short as 1.4 milliseconds, corresponding to rotation, speeds approaching 25% of light speed at the neutron star's equator. At such extreme rotation, the neutron star bulges noticeably at its equator due to centrifugal force, and general relativistic effects become important in describing its structure. Pulsar timing has also contributed to the search for gravitational waves at very low frequencies. By monitoring many pulsars spread across the sky for years, astronomers can detect correlations in the timing variations that would indicate space-time ripples passing through our galaxy. These pulsar timing arrays have placed stringent limits on the gravitational wave background from supermassive black hole mergers throughout cosmic history and may eventually detect such waves directly, opening another window into the universe's violent past. The chemistry of planetary birth. The discovery of the moon-forming disk around the exoplanet CT Char B provides insight into processes occurring around young planets. The disk's composition, particularly its carbon enrichment relative to oxygen, suggests that volatile ices and organic compounds are abundant in the planet-forming region. This has implications for understanding how moons around gas giant planets might acquire the chemical ingredients necessary for habitability. In our own solar system, Jupiter's moon Europa and Saturn's moon Enceladus both harbour subsurface oceans beneath icy crusts, making them prime targets in the search for extraterrestrial life. The chemical composition of these oceans depends on what volatile compounds were available during the moon's formation and what chemical processing has occurred since. If the circumplanetary disk around young Jupiter was carbon-rich, Europa's ocean might contain significant dissolved organic compounds that could serve as nutrients for potential microbial ecosystems. Observing circumplanetary disks around exoplanets allows astronomers to test whether moon formation follows similar processes across different planetary systems. Do all gas giants form extensive moon systems, or does this require specific conditions? How does the composition of the circumplanetary disk relate to the composition of the protoplanetary disk that formed the planet itself? What determines whether moons retain atmospheres and whether they might maintain habitable conditions? These questions connect to broader issues about the prevalence of potentially habitable environments in the universe. Earth-like planets orbiting in habitable zones represent one possibility, but large moons around gas giants might offer another. Such moons could receive tidal heating from gravitational interactions with their host planet, providing an internal heat source independent of stellar radiation. This could maintain subsurface oceans even in systems where the planet orbits well outside the traditional habitable zone. The detection of the disk around CT Char b required exceptional sensitivity and angular resolution. The disk spans only a tiny fraction of an arcsecond as seen from Earth, and the planet itself is much fainter than its host star. JWST's infrared instruments could detect the disk by observing at wavelengths, where the disk's thermal emission is relatively strong compared to the star's light and the planet's reflected light. Future observations with even more powerful instruments might reveal the disk's detailed structure, perhaps even detecting gaps that would indicate moons are already forming. The message in ancient starlight. As we synthesize these many discoveries, a pattern emerges about how cosmic history can be read in the light reaching us from different epochs and environments. The most distant supernova tells us about stellar evolution in the universe's infancy. The awakening black hole reveals how dormant galactic nuclei transition to activity. The ancient stars in the Milky Way's halo preserve information about the first generation of galaxies. Each observation provides a piece of a larger puzzle about how the universe evolved from its smooth, homogeneous initial state to the complex structured cosmos we inhabit today. This reconstructive process resembles archaeology or paleontology, where scientists piece together past conditions from fragmentary evidence preserved in the present. Just as paleontologists reconstruct ancient ecosystems from fossilized bones, shells, and plant impressions, astronomers reconstruct cosmic history from the light emitted by objects at different distances and therefore different cosmic times. The fossil record of the universe is written in photons that have travelled for billions of years to reach our telescopes. But unlike terrestrial fossils, which preserve only certain aspects of ancient organisms, light carries remarkably complete information about its source. Spectroscopy reveals the chemical composition, temperature, density, and motion of the emitting material. The intensity at different wavelengths indicates the physical processes generating the radiation. Polarization measurements probe magnetic fields and geometric structure. By extracting all this information from the light of distant objects, astronomers can reconstruct not just that something existed billions of years ago, but precisely what conditions were like in that distant time and place. The challenge lies in correctly interpreting these signals. Photons travelling across cosmic distances pass through intervening material that can absorb, scatter, or distort them. Gravitational lensing by foreground matter bends light paths and magnifies or distorts images. The expansion of space itself stretches wavelengths and dilutes photon density. Distinguishing genuine properties of the source from artifacts introduced during the light's journey requires sophisticated analysis and careful modelling of all possible effects. This is why discoveries often require years of follow-up observations and analysis before the community reaches consensus about their interpretation. The initial detection suggests something interesting, but confirming it requires ruling out alternative explanations, accounting for systematic effects, and gathering independent evidence from different observing techniques. The scientific process advances not through dramatic revelations, but through patient accumulation of evidence that gradually constrains interpretations until only one explanation remains consistent with all observations: the symphony of multiple messengers. One of the most profound shifts in astronomy over the past decade has been the emergence of multi-messenger observations, the practice of studying cosmic events using not just light across different wavelengths, but also gravitational waves, neutrinos, and even cosmic rays. The discoveries of 2024 and 2025 demonstrate how this approach has matured from an aspiration to standard practice, with major findings routinely involving coordination between dozens of observatories operating across the full breadth of accessible observation techniques. The record-breaking supernova detected at cosmic dawn exemplifies this approach. The initial gamma-ray burst was detected by a dedicated gamma-ray monitor in space. Within minutes, automated systems notified optical and infrared telescopes around the world, which began tracking the fading afterglow. Spectroscopic observations measured the redshift and identified the burst's extreme distance. Days later, JWST observed in infrared, revealing the supernova's detailed properties. Each observation provided information no single instrument could capture alone, and only by combining all these data could astronomers fully characterize this distant explosion. Gravitational wave astronomy represents perhaps the most significant addition to the multi-messenger toolkit. Since LIGO's first detection of merging black holes in 2015, gravitational wave observatories have detected dozens of merger events, providing information about compact object populations and testing general relativity in the strong field regime. When stellar mass black holes or neutron stars merge, they produce gravitational waves that carry away orbital energy, eventually bringing the objects together in a final catastrophic coalescence that releases more power than all the stars in the universe combined, but for only a fraction of a second. The detection of gravitational waves from neutron star mergers has proven particularly valuable because these events also produce light. When two neutron stars spiral together and merge, they create conditions of extreme temperature and density that synthesize heavy elements through rapid neutron capture, the R process that produces roughly half of all elements heavier than iron. The merger also launches jets of material at relativistic speeds, producing gamma-ray bursts and radioactively glowing kilonova emission visible for days after the event. By observing both gravitational waves and light from the same event, astronomers can determine the distance independently using both methods, providing a new way to measure cosmic expansion. The promise of multi-messenger astronomy extends to even more exotic signals. Neutrino observatories like IceCube, which uses a cubic kilometre of Antarctic ice as a detector, can observe high-energy neutrinos produced by cosmic ray acceleration in extreme environments. When an astrophysical neutrino is detected, its arrival direction points back toward the source, allowing optical and other telescopes to search for the counterpart. Several such coincident detections have occurred, revealing active galactic nuclei and other energetic sources as neutrino emitters. Future multi-messenger observations will involve even more sophisticated coordination. Next-generation gravitational wave detectors currently under construction will be sensitive enough to detect neutron star mergers throughout the observable universe. When combined with optical observations from JWST and next-generation extremely large telescopes, these detections will provide unprecedented insights into how heavy elements are produced and distributed throughout cosmic history. The dream is that by observing the universe through every available channel simultaneously, we can achieve a comprehensive understanding that would be impossible from any single type of observation. The engineering of discovery. Behind every astronomical discovery lies extraordinary engineering that makes the observations possible. The instruments detecting these phenomena represent some of humanity's most sophisticated technical achievements, pushing the boundaries of what's physically possible within the constraints of available materials, manufacturing techniques, and budgets. Understanding these technical aspects provides important context for appreciating both what we can observe and what remains tantalizingly beyond our current capabilities. Consider the James Webb Space Telescope, which has featured prominently in many 2024 to 2025 discoveries. JWST's development spanned more than 2 decades and cost approximately $10 billion, making it one of the most expensive scientific instruments ever built. Every aspect of its design required solving problems that had never been solved before. The segmented primary mirror, for instance, needed to deploy reliably in space and then align, to nanometer precision despite launching folded inside a rocket and experiencing dramatic temperature changes. The solution involved actuators behind each mirror segment that can adjust its position in 6 degrees of freedom, guided by sensitive wavefront sensors and sophisticated control algorithms. The sunshield that keeps JWST cold enough for infrared astronomy required developing new materials that could survive launch while remaining flexible enough to deploy in space. Each layer consists of a thin film of kapton coated with aluminum and doped silicon, chosen for its combination of strength, thermal properties, and resistance to degradation from solar ultraviolet radiation. The layers are separated by precisely calculated gaps that allow heat to radiate away efficiently while preventing any single layer from heating the others through conduction or convection. During deployment, hundreds of motorized mechanisms had to function flawlessly despite never being tested altogether on Earth. True space conditions cannot be perfectly simulated on the ground. Ground-based telescopes face different challenges. The Atacama Large Millimeter/Submillimeter Array, which observed convection cells on the surface of our Doradus, consists of 66 antennas spread across the high desert of northern Chile at an altitude exceeding 5,000 meters. Operating at such altitudes presents significant challenges. The thin atmosphere makes it difficult for personnel to work, and the extreme dryness, while beneficial for millimeter wave observations, requires special materials and procedures to prevent equipment degradation. Each antenna can be physically moved to different locations on the site using specialized transporters, allowing astronomers to reconfigure the array's geometry to optimize resolution or sensitivity depending on the scientific goal. The data processing required for modern astronomical observations represents another engineering challenge. JWST generates tens of gigabytes of data during each observation, all of which must be transmitted to Earth, processed through multiple calibration and analysis pipelines, and archived for future use. The processing removes instrumental artifacts, corrects for known systematic effects, and produces scientifically useful data products, images, spectra, light curves. This processing requires enormous computational resources and sophisticated software developed over many years by teams of programmers and instrument scientists. The coordination between multiple observatories for multi-messenger observations requires real-time communication systems and rapid response protocols. When a gamma-ray burst is detected, automated systems must immediately calculate its position and distribute alert notices to observatories worldwide. Telescopes must rapidly interrupt their scheduled observations, slew to the new target, and begin taking data within minutes. Acquiring and analyzing initial observations, distributing results, and coordinating follow-up observations all happen on timescales of hours, while the event is still ongoing and evolving. This requires not just technical systems, but also international cooperation and agreed-upon protocols for data sharing and publication. The development of new instruments continues to push boundaries. The extremely large telescope currently under construction in Chile will have a primary mirror 39 meters in diameter, composed of 798 individual segments. The adaptive optic systems required to compensate for atmospheric turbulence and achieve diffraction-limited resolution will be the most advanced ever built, using multiple laser guide stars and real-time wavefront control with thousands of actuators. When operational in the early 2030s, this telescope will be able to directly image Earth-sized exoplanets around nearby stars and study the atmospheres of these worlds in search of biosignatures. Space-based gravitational wave observatories like LISA, planned for launch in the 2030s, will consist of 3 spacecraft flying in formation millions of kilometers apart, using laser interferometry to measure distance changes smaller than the width of an atom. The technical challenges include maintaining stable orbits, eliminating all possible sources of noise and vibration, and achieving laser frequency stability far exceeding what's possible with current technology. Success will open a new observational window, spanning frequencies from millihertz to hertz, allowing detection of supermassive black hole mergers throughout the universe, and potentially revealing gravitational wave signals from the Big Bang itself. Each new generation of instruments extends our observational reach, revealing phenomena that previous generations couldn't detect, and often discovering surprises that weren't anticipated. This progression, from Galileo's first telescope observations 4 centuries ago through today's space observatories and gravitational wave detectors, represents humanity's expanding capability to gather information about the universe. Yet each advance also reveals new mysteries and asks new questions, suggesting that the process of discovery will continue indefinitely as our technical capabilities grow. The conclusion: the expanding horizon of mystery. What has shifted in our understanding over these 2 years isn't any single fact, but rather our relationship to cosmic uncertainty itself. We've grown accustomed to viewing the universe as largely comprehended, a place where the broad outlines of cosmic history are known, even if details remain to be filled in. The discoveries of 2024 and 2025 suggest this comfortable position may be premature. The cosmos appears to be more dynamic, more violent, more chemically complex, and perhaps more alive than our theories comfortably accommodate. Consider what it means that dark energy might vary across time. If confirmed, this doesn't merely adjust our model of cosmic expansion, it fundamentally challenges our understanding of what vacuum energy is and how the universe will evolve billions of years into the future. The heat-death scenario, where expansion continues accelerating until galaxies become isolated islands separated by unbridgeable voids, might not be inevitable. Alternative futures become possible, some perhaps more hospitable to the long-term persistence of complexity and structure than the bleak endings we've envisioned. The presence of supermassive black holes when the universe was barely 500 million years old forces us to confront how little we truly understand about the first chapters of cosmic history. Were there massive seed black holes formed through direct collapse? Did population 3 stars create black hole remnants far larger than anything we observe today? Did accretion proceed through mechanisms we haven't discovered? Each possibility opens new questions about the physical conditions in the early universe and the processes that transformed the nearly uniform soup of hydrogen and helium created in the Big Bang into the structured cosmos we inhabit. The potential biosignatures on K2-18b and Mars present perhaps the most profound implications for how we understand our place in existence. If life arose independently on Mars during its ancient wet phase, then the origin of life cannot be an extraordinarily rare event requiring exceptional circumstances. It would suggest that wherever liquid water persists in contact with energy sources and chemical nutrients, biology might emerge given sufficient time. This wouldn't prove life exists elsewhere in the universe today, but it would shift the question from "does life exist elsewhere?" to "where else does life exist, and what forms might it take?" The runaway black hole racing through intergalactic space at millions of miles per hour, leaving a glowing trail of compressed gas in its wake, reminds us that the universe contains violence and drama on scales we can barely imagine. The merger event that created this object and ejected it from its home released more energy in gravitational waves than all the stars in the observable universe emit as light. It represents a cosmic catastrophe that transformed the entire galactic environment, potentially disrupting star formation, triggering new bursts of activity, reshaping the distribution of matter across hundreds of thousands of light years. These are not merely scientific curiosities or abstract puzzles for specialists to solve in journals. They're invitations to reconsider what we think we know about existence itself, about the conditions that permit complexity and consciousness to emerge from fundamental physics, about the ultimate fate toward which everything we observe is evolving. The universe has revealed itself to be stranger and more surprising than we anticipated, which suggests our current theories and models, for all their sophistication and predictive success, remain incomplete approximations of a deeper reality we've yet to grasp. As you consider these discoveries and their implications, lying perhaps in darkness beneath the ceiling that represents an infinitesimal fraction of the space between Earth and the nearest star, which itself represents an infinitesimal fraction of the distance to the galaxies hosting infant supermassive black holes, remember that this knowledge has been accumulated photon by photon, measurement by measurement, through the patient work of thousands of researchers across generations. Each discovery rests on foundations of theory, observation, and technology that required lifetimes to construct. The light from that record-breaking supernova travelled for more than 12 billion years across expanding space, carrying information about stellar death in the universe's youth. It crossed distances so vast that if you could somehow travel at light speed, the journey would consume more time than the entire history of Earth from its formation to the present. Yet that light arrived, was collected by instruments of exquisite sensitivity, and revealed its secrets to minds evolved on a small planet orbiting an unremarkable star in the suburbs of an ordinary galaxy. This represents something extraordinary. The universe has arranged itself in such a way that structure forms, complexity emerges, consciousness develops, and understanding becomes possible. We exist at a moment in cosmic history when stars still burn, galaxies still form, and the evidence of the universe's origins remains visible in the sky. Billions of years in the future, if the dark energy results prove correct and expansion continues accelerating, our descendant civilizations, should any exist, will observe a much lonelier cosmos, with most galaxies having receded beyond the visible horizon. We are witnesses to a universe still young enough, still structured enough, still transparent enough that its history can be read in the light that reaches us. Every observation, every detection, every careful measurement adds to a collective understanding that began when our ancestors first looked up and wondered what those lights in the darkness might be. The questions have grown more sophisticated, the instruments more powerful, the answers more mathematically precise. But the fundamental impulse remains unchanged. We look outward to understand where we are, what we're made of, and what role we might play in the vast unfolding of cosmic time. The discoveries of 2024 and 2025 remind us that this understanding remains far from complete. The universe continues revealing new mysteries, new questions, new invitations to wonder. In the quiet darkness, beneath stars whose light left its source before our ancestors discovered fire, we continue the patient work of deciphering messages written in photons across billions of years, gradually assembling a picture of reality that grows stranger and more beautiful with each passing year. We find ourselves suspended in a moment between what we've learned and what remains unknown. Between the past we can observe receding into cosmic distance, and the future that remains tantalizingly uncertain, watching as the universe slowly reveals itself to be far more mysterious than we ever dared imagine